Hello everyone, hopefully you're doing well. In this video, we're going to continue with chapter 2, functions in graph. But in this particular section, what we're going to see is transformation of functions. So probably you already see some transformation of functions before. We're going to recognize some graphs of common functions, use vertical shifts to graph functions, use horizontal shifts to graph functions, use reflections to graph functions, use vertical strength, stretching, and shrinking to graph functions, etc. So this is the objectives for these sections. Without further ado, let's start first of all by graphs of common functions. So what are the graphs of common functions? So we said there are, we can say there are 7 functions that are frequently encountered in algebra. So probably you heard about some of them before, kind of a graph, graph of a constant functions, like if you have, um, let's see, where is my pencil? Okay, okay, I think I see where I am. All right, the pencil was right there. Now I can see it. All right, so we're gonna keep the pencil. Let's use red instead. Right. Constant is like you have f of x equal simply, for example, 2. To graph a functions like this, all you need to do is identify where is 2. 2, let's say 1 and 2. So that gives you a horizontal line if f of x equal 2, or when we say f of x equal 2, is that for us the same thing saying y equal 2. All right, or it can be x equal 1. Now the other functions you can see is functions that we can call identity functions. Let's say for a constant function, the domain and the range, domain is all real numbers. The range is only a single number at this point. So, and constant on all real numbers. I mean, and negative infinity and infinity. It's an even functions. The same thing, the identity functions. So you see the identity is okay, f of x equal x. So at this point, if you try to graph f of x equal x, what happened? You can even construct a small table. If x is 0, y is 0. If x is 1, y would be 1. Or if x is negative 1, y would be negative 1 in a function like this. So we see the graph would go through the origin for a f of x equal x. Now, absolute value functions, usually it's well, for the identity functions, the domain and the range would be all real numbers, with no problem with that. And for an absolute value functions, it's simply a V shape. If you graph an absolute value functions, it would be a V. For example, an absolute value functions like f of x equal absolute value of x. If x is 0, y is 0. If x is negative 1, y would be 1 because absolute value of negative 1 is 1. If x is 1, y would be 1. If x is negative 2, y would be 2. So that's why you see, actually, it's not a parabola, but it's a V shape. That's a V shape. This is absolute value functions. But if for a quadratic functions like the standard one, you see, if you have x squared, then x squared would give you a function that has a parabola. So parabola is like it's a U shape. The U shape, for example, if x is 0, y would be 0. If x is 1, y would be 1. If x is negative 1, y would be negative 1. You see the difference between absolute value functions and standard quadratic functions is because, let's say, if x is 2, for absolute value. If x is -2, y would be 2. If x is 2, y would be 2. But in the quadratic functions, if x is -2, y would be 4. And if x is 2, y would be also 4. So this one right there doesn't give us a V, but a U shape, like a parabola open up because the coefficient of x squared is positive. So there is no negative before the x squared. So if functions like this, as you can see, the domain would be all real numbers, but the range would be 0 to infinity because we cannot go any lower than 0. On the y-axis because it's a U-shape. We have one turning point. There is nothing else we can do with that. And if we do, square root functions, I try to do a very small one for you for each of them. Square root functions, it's grow at a way like let's say if x is 0, square root of 0 is 0. If x is 1, square root of 1 is 1. If x is 4, this one would be simply 2, so that's why, you will see we have a shape like this for a, what square root functions. For standard cube root, cube functions, we have two turning points. If we have power 3, then we're gonna turn 2 times. But now you can, in order to graph functions like x power 3, the most important is to identify your x intercepts. But because only x cubed, you can say, oh, if x is 0, we're gonna go through 0. If x is 0, y would be 0. But if x is -1, y would also be -1. If x is 1, y would be 1. But look, if x is 2, y would be 8 because 2 power 3 is 8. So it's going to have something very odd. And if x is -2, y would be -8. So that's why you see this graph would goes from the negative infinity going to 1, 1 and go up, And then, cube roots is like you have 2 square roots, cube roots, if you see, if x is 0, we're gonna eventually go to 0. If x is 8, for example, x is 8, what will be cube roots of 8? Yeah, that would be 2. And if x is -8, so it's give it -2. So that's why in order to graph a function like that, just take 1 or 2 points, to graph just the standard functions. So that would be the cube roots, right? Now, you see for each of them how that's work. And looking at the graph, you can identify the domain and the range. Remember, the domain is all about x values, what the smallest and largest value x can take. You'll see for all those graphs, the domain would be all real numbers. There is no restriction for x except for the square root, because the square root of a negative number is not a real number. So at this point, for the square root functions, you see the domain would be 0 to infinity because we cannot go any lower than 0 on the x-axis. It's the same thing for y also. Y would never be negative because the square root of a number is not negative. At this point, you see the domain and the range, both of them will start from 0 to infinity. Otherwise, for the standard quadratic function, so the range start from 0 to infinity. For the absolute value functions, you can see it start from 0 to infinity. That can change at any time. But for the other functions, especially when it's linear, you can see that it is all real numbers for both of them. Now, we do have a few graphs to show you the difference. I wanted to introduce these to you in a certain way that I graph them myself. But look, in the book, you do have all these graphs. Look at the first one. F of x equal, C is known as the constant function. The domain of these functions is all real numbers, and the range of these functions is C, all right? So, because we're not gonna go any lower than that, it's just C, all right? Because if C is a number, right there, you have a feeling they ask you to graph something like f of x equal 1/2. No, 1.5, right? That's 1.5 or 3/2. Maybe it's 3/2. All right, so we have that functions. The next one would be a functions where you only ask you to graph f of x, because if you plug x equal 1, you see, you have 1. If x is 1, then it gives you y would be 1. If x is -1, y would be -1. We can see that in that functions where you said f of x equal x, xy. If x is -1, this one will be -1. If x is 1, this would be 1. If x is 0, that one would be 0 when you plug it in the functions. So the domain and the range, they are all real numbers. Now you can see these functions totally increase. It's not decreasing because it's rise from left to right. It's increase, and it's an odd function because it goes opposite directions. This one is an even, right? Now look at the absolute value functions we just talked about. It's a value. The domain would be all real numbers, but the range would be from 0 to infinity, including 0. 0 is included. Uh, you know, the functions is decrease. You see decrease, remember you go from up to down, so that's decreasing, and that's the increasing function. So it's decrease on negative infinity to 0 and increase 0 to infinity. These functions also even because it goes same directions. These functions are quadratic functions, also even because same directions. It's all real numbers. When we say all real numbers, I mean negative infinity to infinity for the domain. The range, you see, when the graph goes down, goes through zeros, would never go back again. So at this point, we consider that the function, the domain, the range would be 0 to infinity. That's the lowest point we can go, 0 to infinity. Never put infinity to 0 unless it's negative infinity to 0. So it's 0 to infinity. We put it in order. The functions decrease. You can see the decreasing. The interval is decreased. Remember, it's decreased up to 0 when x is 0, and it started from the negative infinity. So, and it's increased from when x is 0 and going to a positive infinity. All right. So now that you see how this works, how about the next one we talked about is the square root functions. The square root functions, the domain is 0 to infinity and the range is 0, because we would never go in the negative, as you cannot take the square roots of a negative number to obtain a real number. So domain and range would be all real numbers. The function is increasing, so it's not decreasing. It's only continue to increase. We have other ones you have is actually this function is odd because you're not going both directions anyway. You have um you know the standard cubic functions. We went over this already. you have an idea of how that's working. The domain is all real numbers and the range are all real numbers. There is no restriction for X values to plug in this function. And this function is odd because it goes opposite directions. Last one we covered that because we give you, as we said, those are the standards one, right? So we said the 7 frequently encountered functions in algebra. So, it shows functions graph and lists characteristic of those functions, the shape of each graph and, very important to remember. Like this one is cube root functions. The cube root functions, you can see in this one, when you cube roots can accept negative numbers for x, all right? Because cube root of -8, what number you multiply by itself 3 times to obtain -8 is -2. But what is the square roots of -4? There is no two numbers you can multiply to obtain a negative number. There is no number you can multiply by itself to obtain a negative number, right? So because if you do -2 times -2, it's gonna give you +4. So that's why you said you cannot take the square root of a negative number, but you can take the cube root. Or if the index is odd, like cube roots, fifth root, seventh root, ninth root, 8, 10, 11 roots. So if the index is odd, then you can take the square root of a negative number. All right. Hope you like that. The next things we're gonna talk about is really the vertical shifts. We're gonna start by looking at some graphs, because the vertical shifts is very important. All right. So if you let f be a function and c a positive real number, the graph of y equal f of x plus c is the graph of y equal f of x shift c unit vertically, right? Let's say, for example, remember we graph, you know, f of x, right? F of x equal x. This is f of x. Remember in this one, we said if x is 0, y would be 0. If x is 1, y would be 1. If x is -1, y would be -1. So we could graph that from this is f of x, right? So this one right there is f of x equal x. Now, if you change it, let's suppose you said that you want to do f of x equal x plus 1. See, you need to shift your graph vertically 1 unit up. That means if x is 0, y would be 1. If x is 1, y would be 2. If x is -1, y would be 0. See? Exactly the same shape, but we shifted 1 unit, okay? Vertically. We shifted 1 unit vertically, all right? 1 unit up, okay? Because that's the same graph. That's what we're trying to show you. Okay. Give me a second because I think it disconnect me. Yeah, so okay, another shift. Give me 1 second. I try to reconnect with my pencil. So okay. All right, so we're gonna do that. Now, the next one, okay, pencil work now. We're gonna try these examples. These examples is all about how to graph an absolute value functions. First of all, you know how to graph only absolute value. We can just go and try that one. Sorry for the line. I'm trying. I think my pencil is giving me some very hard time. Okay. Okay, we're gonna do that like this. Okay. Now let's suppose you can construct a small table with x and y values, right? X and y. If x is -3, -2, -1, 0, 1, 2, and 3. So I suppose I take these numbers. So if x is -3, you see this one would be 6. If x is -2, you're gonna have 5. -1, that gives you 4, 0, 3, 1, 4, and 2, 5, and 3, 6. The things you need to verify here is the vertex. That means what is the turning point? What is the one that is different? Is only 0, 3. So we know 1, 2, and 3 would be our, when x is 0, y is 3. When x is negative 1 or x is 1, y is 4, right? Y is 4, it's 4. Okay. When x is negative 2 or 2, y is 5. When x is -3, I think I just take negative between -3 and 3. But if you want to go further, you can. There is no limitation on how many points. As long as you remember what is the shape of the graph. If you remember what's the shape of the graph, it should be all fine. So when we graph, this is a V shape. Oh, okay, I think I didn't do that one properly. Let's try again. Okay, consider those lines very straight. So we will say those are the V shape. To graph, when you graph an absolute value of functions, the graph is a V shape. Now, for horizontal, you see we shift, because if you graph only the this one right here is f of x equal absolute value of x plus 3. In this case, if you were graphing only f of x equal absolute value of x, you know the vertex would be at the origin, because when x is 0, y would be 0. When x is -1, y would be 1. When x is 1, 1. When x is 2, you are going to have 2. When x is -2, you are going to have 2, etc. So you know this graph right there would have been, f of x equal absolute value of x. So you see, we shift the graph up. But some other graph might request we do horizontal shift. So what is the horizontal shift? The horizontal shift, what that's the one we're gonna do. When if you let f be a function and c a positive real number, the graph of y equal f of x plus c is the graph of y equal f of x shift to the left c. All right, that's very important to see. For examples, you can have f of x equal x squared, or you can have f of x equal x minus 2 square, you see? So we can shift horizontally, or I can say plus 2. square or plus 3 or minus 3, you know, it doesn't matter what you do, but you can shift it. The graph of y equal f minus c is the graph of y equal f of x shifting to the right. You see, if it's a positive, we could say f of x equal x plus 2 square. We shift it to the left. And if it's negative, we shift it to the right. How we can do that? Many functions. The first one, let's go with an examples right there. For these examples, it asks you to graph f of x equals square root of x. So if we graph f of x equal f of x equal square roots of x, the first thing to do at this point is to graph, you know, is construct a small table xy. If x is 0, because we cannot plug any other number. If x is 0, then y would be 0. If x is 1, f of 1, square root of 1 is 1. If x is 1, y would be 1. Okay. If x is 2, we're going to have square root of 2, but I prefer to say if x is 4, y would be 2, because square root of 4 is 2. 2, 3, and 4. So we're going to say this one is 2. At this point, you have an idea what the graph would look like, okay, to do f of x, okay, to do f of x equal square roots of x. Now, let's do the same for f of x equals square roots of x minus 4. F of x equals square root of x minus 4. We said if x, because now, look at that functions. X cannot be 0. X cannot be any negative number. X cannot be 2, 3. The first number x can be is you know, is 4. So that means we shift our graph horizontally 4 units to the right, okay? Because the first number you can get, if x is 4, 4 minus 4 is 0, square root of 0 is 0. So this is where we're gonna start with this graph. We shift 4 units to the right. If x is 5, 5 minus 4 is 1, square root of 1 is 1. So you see, if x is 5, so we're gonna say this is it. All right. Now, if x, I like to take big numbers. If x is 9, 9 minus, oh no, if x is 8. 8 minus 4 is 4, square root of 4 is 2. So 6, 7, and 8, you see this one right there would give me this. So this would be the same graph, but shifting, we can say 4 units to the right when we take the square root of x minus 4. Please pause the video at any time to review and make sure you understand what we're talking about, okay? That's giantly important. Now, we have some other functions you can see also from here, okay, because we do more than one graph. All right, we can see over there also with example 3 that you know, we can just shift it. Also, this one is outside. If we take the exact same graph, so if we take the exact same graph, all right, we know that yeah, if x, because if we do square root of x first, because this is the first thing we need to do, square root of x. So we have Yeah, sorry for my cat. My cat keep making noise. Okay. Now, if we have if square root of 0 is 0, square root of 1 is 1, square roots of 4, 2, 3, and 4 is 2. So we're gonna have something like that. Now, this is f of x equals square roots of x, okay? F of x equals square root of x. All right, my bad. Sorry. My cat. Okay, now for the second one, you can see if we do xy for these functions right here, remember we're doing this one right there. I'm gonna just change the color and make sure we can do it in green. So if x, you see under the roots right there, x cannot be 0, because if x is 0, we're gonna have 0 minus 1 would be square root of -1 is not a real number. We need to start with, for example, you know, x, all right? We're going to start with something like, can we do that? Yeah, I think we can. We're gonna do, that's reflection. So because we're gonna do, if x is 1, 1 minus 1. If x is 1, 1 minus 1, 0. Square root of 0 is 0. So we're gonna have -2. So when x is 1, y is 1 and 2. That would be -2. All right. If x is 2, 2 minus 1 is 1. Square root of 1 is 1. 1 minus 2 is -1. So x equal 2, y is, all right. You see that? Now we can continue. If x is 5, 5 minus 1 is for square root of, okay, square roots of 4 is 2, 2 minus 2 is 0. So when x is 5, y is 0. So you see, we can continue this graph going like this. Okay. I'm pretty sure if you use your calculator, it will help you to see it better the way we do it. But know that this is really something that show you the, how you shift your graph horizontally. All right. Now, other graph you can see is the reflections, because I didn't go over reflections yet. The graph of y equal negative f of x is the graph of y equal f of x reflected about the x-axis. So the reflection about the y-axis is the graph of y equal f of negative x is the graph of y equal f of x reflect about the x-axis. So I know we need to go over an example for you to see what we are talking about. Let's look at this example. So what you can do about this one. We said that the reflections, as we say, first of all, we can graph cube root of x. Remember how to graph cube root of x? We did that before. We said for cube root of x, because if you plug 0, it's gonna be 0. I'm gonna just change the color. If we plug 0, it's gonna give us 0 for these functions, right? Cube root of 0 is 0, okay? And you said if you plug 1, cube root of 1 would be 1. If you plug -1, cube root of -1 would give you -1. But look, if I don't like to deal with decimal, that's why I don't take -2, -3, -4. What I would do, I'll take -8. If x is if x is -1, 2, 3, 4, 5, 6, 7, 8, y would be -2. So when if you do cube roots of -8, it gives you -2. If x is 8, 1, 2, okay. Yeah, we said 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. That would give us a 2. So this is the graph. As we said, you go this way. Remember, this is f of x equals cube roots of x. Now, what we can do when it is square root of -x, that would be a little bit different. Let's do, if x is 0, y would be 0. If x is 1, if x is 1, y would be -1, you know. But if x is -1, that y would be 1. See, it's just a reflection. The same way, if x is 8, cube roots of 8 would give us -2. Cube root of negative. If x is -8, negative give you positive. Cube root of +8 would be negative. So 2. So that's why we said the graph would be it's just a reflection of the other ones. I know I may not do it properly, but it's just a sketch. Okay, so that would be the reflections for these two graphs. All right, so graph of y equal cube root of x reflects about the axis. Okay, the y-axis. It reflects about the y-axis. So vertically stretch. Also, we can look at this. If you let f be a function and c a positive real number, if c is greater than 1, the graph of y equals c of x is the graph of y equal f of x vertically stretch. You just stretch it, make it big. Like if you have, you know, f of x equal x squared when you graph it, f of x equal 2x squared would be different. Okay, f of x will be 2x squared would be different. All right, let's see it different ways. Okay, we're gonna see it different ways for the next examples. This is what you have. As you can see, we have this beautiful exercise. Use the graph of f of x equal absolute value of x to obtain the graph of f of x equal to absolute value of x. You just multiply it. You know, if we look at it this way, what would you see? All right, let's do f of x equal absolute value of x first. Suppose this line is very straight. Now, if I take a different color, I would say absolute value of x. If x is 0, it gives you 0. If x is 1, it would give you 1. And, all right, if x is -1, it would also give you 1. If x is 2, you're going to have 2. If x is -2, it would be also 2 because absolute value of -2 is 2. So remember, a absolute value function has a V shape. This is a V shape, so that means this is f of x equal absolute value of x. But when you look at these functions right here, if x is 0, definitely y would be 0 because, you know, absolute value of 0 is 0, 2 times 0 is 0. If x is 1, absolute value of 1 is 1, but 2 times 1 is 2. This is what we're going to have. Okay? And then if x is -2, -1 is going to give you 1. 2 times 1 is 2. If x is 2, absolute value of 2 is 2. 2 times 2 is 4. 3 and 4. -2 would also give you a 4. So that's why you would see your v, it's like it's shrunk. It's not stretch, it's shrunk. This is the functions f of x equal to absolute value of x. Yeah, you have two functions like this, right? One of them was something we did, you know, where we have to stretch the graph vertically. Now we can also stretch the graph horizontally. All right. So if you try to stretch the graph horizontally, what you need, you know, it's possible to stretch it and shrink it horizontally. If you let f of x be a function and c a positive real number. If c is greater than 1, the graph of y equal f of cx is the graph of y equal f of x horizontally shrink by dividing each of its coordinate by c. All right. So, you know, if you have f of x equal 3x, right? For us, you know, you can see that like in another function. But you know what? Let's do it in a examples just to show you what we mean by that. Okay. Now, what we see here, we ask you to graph f of x. Okay. Ask you to graph f of x equal x squared to obtain the graph of g of x equal 1/2 of x squared. So first of all, you know if you graph f of x, it's a parabola, right? It's a parabola with, you know, if you have f of x equal x squared, you know if you construct a small table xy, x -2 give you 4, -1 give you 1, 0 give you 0, 1 give you 1, and 2 give you 4, right? In the because power 2, -2 power 2 give you positive. So if you graph between -1 and -2 and 2, so 1, 2, 3, and 4, you know 1 give us 1, 2 give us 4, 1, 4. Okay, so we can have it this way as well. Okay, now we know it's a parabola, not a V, so our graph would be no. Yeah, I'm terrible in graphing with my pencil, but we're gonna try it again. Okay, let's try it. So what we mean by that, our vertex is at 0, 0. But okay, this is a sketch of the graph. Now, look what's happened when we have 1/2. Okay, I'm gonna put it with a different color. Let's choose green. Okay, with f of x, we're gonna say 1/2 x power 2, g of x equal that. So if x is 0, we're gonna take -2, -1, 0, 1, and 2 as well. If x is -2, 1/2 of -2 is -1 power, that's give you only 1. -1 give you 1/4 positive. 0 give us 0, 1 give us 1/4, and 2 give us 1. If you want, we can even add 3. No, we can add 4. If x is 4, 1/2 times half of 4 is 2, 2 power 2 is 4. Half of or negative 4 would give you 4. So if we go 3 and negative 4, 3 and 4, remember we have f of x 0, 0, we are right there also, but negative 2 give us 1, 2 give us 1, and 4 give us 2. 4 give us 4. So you see, this is our graph. It's really stretched. We're going to stretch it. Stretching. Okay. And you can use a calculator to verify that, because as we said, it's always possible to do some other examples, like these examples. If you want to graph it, that would be all fine. Like, you can either graph, if we graph x squared, let's suppose we graph, if we graph x squared, then x squared goes by the origin. So if x is 0, y is 0. If x is 1, y is 1. If x is negative 1, y is also 1. If x is 2, y is 2, 3, and 4. If x is negative 2, y is also 4 somewhere there. So this is, remember, the standard quadratic functions f of x equal x squared. So this is the f of x equal x squared. Now, with that one, I know it's might require more work, because we're going to graph using a sequence of transformations. You can transform this one multiple ways. The first thing to do, you can either construct you can either construct a table to find those numbers, or for me, what I can do, I know is going to ask me to, you know, to um, to do it, like how I can shift it 1 unit, because remember we said if it's negative, you shift 1 unit to the right. So I can shift it 1 unit. Instead of start the vertex to be at the origin, it's gonna shift to 1, so the vertex would be at 1. I'm not doing it yet, but it says +3, because it says +3. Now I'm not putting the vertex at 1. I need to go 3 units up. 1, 2, and 3. Now, actually, this is where my vertex located. The vertex means the turning point. Okay. Now, from there, I know my graph would turn. The turning point is right there. All I need to do is to find 2 more points. If I plug x equal 2, suppose if I said x equal 2, what x equal 2 would be? Oh, let's say 0. If x is 0, what would be y? See, y would be 5, right? 4 and 5. So that means our graph would go, and if x is 2, this one will also be 5. Okay. Now I give you an idea of the transformations of graph. definitely a functions involving more than one transformation can be graphed by performing transformations in, you can do horizontal shifting, stretching or shrinking, vertical shifting, and reflection. So we call those, all of them, transformations of graph. Hopefully that was very helpful. In a different video, we would come back to do some combinations of functions, especially compositions. Let me know if you have any questions. I'll see you soon in a different video. Take care.